So our last speaker for today is Masahito Yamazaki, who is going to tell us about the
Okay. So while the slide is coming up, like other speakers, it's very much a pleasure for me to thank the organizers for this fantastic event. And also, I'd like to add that it's also very much a pleasure for me to keep coming back to the Strings Conference. And we heard that the Strings Conference seems to be going on for 35 years or so. And I'm not that senior, but I counted, and the first time I came to Strings Conference was 2008. Don't calculate my age. And then, and then each time there are new developments, which I enjoy very much. But on the other hand, it's also true that looking back some of the slides and all that, some fundamental questions remain. And in that respect, I recently came across a proverb in lab, which I hope is correct, which says that patience is the key to relief. And in this spirit, in thinking about this talk, I thought I should talk about some topic which have been keep coming back over and over since I was a graduate student. And I asked myself, what is the topic? And to me, that topic is the counting of BPS states. And I know this is a very diverse conference, but I hope everybody agrees that the counting of BPS states is a very important question. For example, it gives an ingredient to do very precise tests of dualities in string theories and gauge theory, for example. And it gives a microstates of black holes. And also, from purely mathematical viewpoint, it gives a lot of beautiful mathematical structure concerning the enumerative invariance of the geometry, and so on and so on. So there are a lot of motivations. And in this respect, I'm very happy to report that about our new work in this direction, which is in collaboration with Jiakan Bao, who is an excellent postdoc at my institute, and that will appear tonight. So if you want to look at the details, please wait several hours, and we will find all the details, formulas, and everything. And then what I'm going to tell you is partly based on some earlier works. The most recent one is with the Lakjon Song, but also a series of many, many papers together with collaborators, including Dima Garakov, Pei, Hiroshi Oguri, and many other people. So what is the setup? The setup is to compute, we start with Quiver gauge series, or with at least two supercharges. And I'm going to compute some partition function, essentially BPS bit indices or elliptic genuses, and those are the quantities. So the series I'm going to consider is actually very, very, very general, at least by my standard. And for example, this is the example. Well, this looks like a 1D quiver, but the quiver can be more crazy. And with the four supercharges. So you can think of them as a dimensional reduction of the 4D n = 1 theory with the F-term constraints. There could be more even reduced supersymmetry. In this case, there's a unoriented arrow, which is represented by color red here, which is called a Furby multiplet. So these are very, very general setup of Quiver gauge series. And then what is the result? So before coming to the detail, here is the main result. So the first is that you have to compute them, right? So VPS index, so there's the numbers. And there's a set of numbers, so there are infinite set of numbers. And the first question is that, what are they? Give me the number. Is it 10 or 12 or minus 13? And then the first result says that you can, there is a formula. So this is the generating function of all these VPS invariants. And it's given by some statistical mechanical crystal melting, which is defined as some statistical mechanism. So it's a sum over states. Sum over states we call the crystal state. And there's a weight associated with it. And the point is all these ingredients can be computed purely combinatorial. There's already a formula. Whatever quiver you give me, Mojiro-san caveat, which I'm coming to, there is a formula, which you can write down. You can put it on computer. Now, the second result is concerning the algebra. So if you do the computation, you get a lot of numbers. But at some point, you begin to ask, is there any structure? Is there a complicated set of numbers? Is there any structure? And probably there are many, many different ways of answering that question. But one particular way of answering that question is that, is it a character of some algebra? So, and then the second result says that this BPS partition function, which is also crystal partition function, is a character of some algebra. Of Anderson representation R. So, so what is the algebra? Well, it turns out you can construct the algebra, which is a new algebra, which was not known in the literature. And for the reason which I don't explain too much, we are going to call it a double Quiver algebra, because it's some sort of a double of the previously defined algebra. So these are the main points. So let me first explain a little bit more detail of what I mean by counting. So let's see. So of course, the counting problem itself is clear, and then we need some guideline, right? So if you want to compute things, and I have two guidelines in this respect. The first guideline is that for some geometries, this has been computed before, and those are the Quiver gauge series corresponding to toric geometries. There is a torus action in the Calabi-Yau. Toric Calabi-Yau 3 and then the Calabi-Yau 4-fold. And so in the case of C3, there's this celebrated work by Okunko, Freshik, and Buffer, which led to the original model of the crystal melting. And for toric Calabi-Yau 3, in a paper with Hiroshi, we generalized it to more arbitrary toric Calabi-Yau 3. And coming back to that, and we recently had a paper about the toric Calabi-Yau 4-fold case. And in this case, the crystal in question is 4-dimensional. So I cannot even draw it. So this is not a crystal, but just a figure of quiver. But the point is that regardless of the details, the answer is already known in some specific examples. So you expect that maybe something similar might emerge in a more general situation. Now, the second point is that, in a sense, the index has already been computed in a sense. And that's this celebrated JK residue formula. Well, so I know that this is the very end of a long day. So I'm not going to go into all the technical ingredients of this JK residue formula. But let me recap some of the very minimal ingredient of this formula. Well, first of all, this is a multidimensional integral. So we have to do multidimensional complex analysis. It's complicated. But at least under some assumptions, you can evaluate it iteratively. So if there are n variables, you just keep evaluating one by one. So it becomes an iterative integral. So it becomes a little bit more tractable. Now, the second ingredient is there is this eta parameter, which is eta in the literature. Well, technically, it's a duo of the Cartan, etc. Well, the rough physical meaning is that it separates the particle from antiparticle. So we are doing the BPS state counting. So you need to choose a cone and then count the BPS particles. And which cone to choose, that's dictated by this eta. Well, in practice, for the most of my talk, I'm going to choose a very particular eta. Now, there are extra ingredients. For example, the potential function depends on this set of parameters, epsilon, which is the chemical potentials. So if there are flavor symmetry in the theory, you can turn on the chemical potentials. And the residue itself is evaluated at the special points. These are singular points. And then of what? So singular points of the one-loop determinant. So this is the integrand and the singularities. And you take a roughly a set of residues there and sum over. And which sum to take, that's determined by this parameter eta. So that is already a known formula. Now the basic idea is extremely simple. So there is already a formula. And so that means that if you study this for a long time, it really looks like this is similar to the structure I was talking about. So namely, you want to regard this sum as a sum over the so-called crystal. So you define the crystal from this data. And there's going to be a residue from there. And that's going to be the Boltzmann weight. So that's a very basic idea. And well, probably many of you have heard about the Nekrasov partition function for instant counting. And Nikita derived this formula by using essentially this type of logic. In his case, that was 8 supercharges. But I'm discussing much more general class of theory with much more reduced supersymmetries. So, well, let me try to explain even a little bit more detail. So, well, first of all, I need to look into what this function is in order to discuss the pole structure. So, well, of course, that depends on what matter content you have. But suppose that there is a bifundamental arrow in between, the bifundamental matter. And then there is a one-loop determinant, which contributes this factor 1 over zeta. And the zeta, well, depending on whether you want to do elliptic genus or width index or zero-dimensional matrix integral, there are a couple of functions which correspond to elliptic trigonometric rational hierarchy. which often appears in these type of topics. But let's say you are interested in the rational case and zeta z itself is z. And then so this is just one over some function which generates the pole. Pole with these parameters which takes values in the current term of the gauge group. So it's very simple. You have a very concrete function, you can look at the poles. Now, let's look at this example. So there's a box represent a flavor symmetry, and then there is a gauge symmetry. This is a very simple quiver with 4 supercharges. And then I'm going to evaluate it using these functions, and then for each arrow there is a set of functions like this. And this contains many, many poles. But suppose that, for example, when you evaluate the first variable, you take a pole from here in this arrow. And in the second step, you take a pole from here. That corresponds to arrow going around here, a joint arrow. And then you can keep going. For example, this third step, you also take a pole from here. And if you evaluate it, the value of this u star, the variable, becomes the b1 plus epsilon 1 to epsilon 2, where epsilon 1 is the parameter for this arrow. And then you can just plot it on this plane. And then what you get is that you just have a vertex, and it keeps going. So epsilon 1, and then twice, 3 times. It just keeps going. And that's the picture you have. And well, if you just look at the pole structure of the previous expression, the actually poles correspond to going backwards too, minus epsilon 1. But they're not taken under this particular choice of eta. So very roughly, intuitively speaking, the positive direction corresponds to a particle, but the other direction corresponds to antiparticle. So we are not taking it. So we get just the one-dimensional structure. Now, this is the simplest example, but you can keep doing this for many other examples. For example, this is an example corresponds to some affine Dinky diagram. It doesn't have to be this theory, but say, for example, this theory. And in the first step, you start from there, this blue box, and you go there. Second step, there are many possibilities. And then I plot them according to the charges. So each of the arrow has the charges, and then depending on that, it points in a specific direction. And going to the third step, and then going to the fourth step, it becomes more complicated, more possibilities. But then I can collect all these ingredients into the single graph, which is this graph. So in this case, it's a two-dimensional picture with a lot of arrows and connectivity in between. So the statement is that since we are looking at the JK residue, this counts the combinatorial structure. So this counts the BPS states. Well, so if you look at the final result and then want to remember how to get the BPS states, you can basically start with the initial atom. For example, in this case, there is a lead bot, and starting from there, going around the arrow, and then take some subset. And so we are calling it a molecule. So each of these vertices are called atoms, and then there you construct a molecule out of it. And if it satisfies some conditions, it's a BPS and include it. So you can write down precise combinatorial rule which matches the predictions or the result of the computation from the JK residue. And we are talking about a specific example, but we can come up with a precise rule which applies to n equal 4 as well as n equal 2 supercharged examples. Now, there is one thing to notice. So everything so far is more or less combinatorial. But of course, you might have to worry a little bit, because, for example, there are clearly examples where supersymmetry is broken. In which case, what I'm discussing this doesn't make sense. And at least there are some counterpart of that. So here, in evaluating the residue, we use the iterative formula. And then there is a subtlety of the JK residue. And very roughly speaking, it's not precise, but whenever higher order poles appear, there are some subtleties in the evaluation of the residue. So in the evaluation of the formula like this, we need to assume that doesn't happen. So that restricts the class of series. So we still have to discuss a gigantic class of series, but not all the series, so that we don't run into contradiction. So this is the counting part of the story. Now, let's come to the algebra part of the story. What is the algebra we get? And here, there is no general result known. So we have to be a little bit hands-on and then try to construct the algebra. But of course, the algebra is going to be complicated, so we need some guideline again. And then the guideline again comes from toric-Calabi manifold. So if you start with the Quiver gauge theory with 4 supercharges, and then suppose that these quivers come from toric-Calabi threefolds, and in this case, the algebra is known by the name of Quiver algebra. So in order to compare with the double Quiver algebra, I might even call it a single Quiver algebra, so that's a different algebra. So there was a single Quiver algebra defined already in the literature. And then there, at least for toric-Calabi 3, with 4 supercharges, a similar story existed already. Namely, there is an algebra, and then the crystals, and action on that, such that the partition function is the character of that. And then this Quiver algebra itself is a well-defined algebra with the generator and relations. And it's a complicated algebra, but it has a known connection to other topics like affine Yang-Yang quantum toroidal. And you can even truncate it, get the corner BOA all the way to WN algebra or Virasoro, et cetera. So it's a just bus generalization of Virasoro in a sense. Well, and of course, the natural choice is that maybe you can try to start with this algebra and then try to act on the crystal I just constructed. That's what I've been doing for a long time. But apparently, there's some obstruction for doing that. So instead, I decided to change the algebra. So I decided to start with the Quiver algebra, original one, but then change it to a new algebra, which we call the double Quiver algebra. And well, of course, this has a more precise meaning. But my at least vague intuition is that it's like here in this original algebra, we included the generator for particles only. But here, I include a generator for both particles and antiparticles. And then, of course, there are many more poles. We are not including everything, so we need to do something to take care of the extra poles. So that's more or less the main idea. So, OK, what is the double Quiver algebra? Well, it's defined by generators and relations. So the generators are, we have a set of generators for each vertex of the quiver. So we have a nodes. For each vertex of the quiver, we have a generator, E, F, psi, omega. And so E and F, E, F, psi, these are like a Shubari generators, as we will see. So E is like an upper triangular part, F is lower triangular part, psi is a Cartan. Now, compared with the previous Quiver Yang-Yang, single Quiver Yang-Yang, we are including extra generator, which also plays an important role. And in order to write down the relations, I introduced some function. The details doesn't matter, but it's written in terms of the zeta, which I introduced previously. For the rational case, zeta z is simply z. And then I can write down the relations. So despite the fact that this is the very last talk of the day, this might be one of the most complicated formulas you've seen today. But please don't be discouraged, because actually the relation hasn't ended. So there is even one more page. But the main point is that there are relations. And OK, so these are like somewhat like OP-type relations you're familiar with in conformal field theory. So these are, each of these generators has a parameter dependent, spectral parameter. You can expand, and then there are it contains infinitely many generators, actually. And so some of the things commute. For example, in the first equations commute. But in other cases, don't. And there are a couple factors like this. And there's a psi tilde. Psi tilde is this gigantic beast. It might not be too elementary if you just stare at it. But the point is that everything is very explicit, which is good for, especially if you're a physicist. I say that because there are some construction of some similar algebras in mathematical literature, but quite often, sometimes things are very abstract. So the important thing is that you can write down everything explicitly at least. And then in this algebra, we haven't done too much, but if you like, you can try to keep truncating to make it something simple. And one comment is that this is not associated with any Lie algebra or anything. It's more like associated with the quiver. So there are all sorts of algebras known in the mathematical literature, quantum groups, quantum affine, et cetera. But all of them are associated with the Lie algebras and deformations, but this is not. And so now we have the algebra. We can go back to the crystal, which we constructed before, and try to let it act. And this is the type of formula you found. So there are Shubari-like generators. They act by creating annihilation operators. So these are like a creation annihilation operators. So remember that we constructed crystal by adding atoms one by one. So these create annihilate atoms. And some of the generators act diagonally. But now this omega takes care of the poles which are not allowed by eta. So these are like antiparticle contributions. And then finally, all these factors here. All these factors psi tilde, and I'm not going to write on the formula, but the important part is that this is also determined by the one-loop determinants of the JK residue formula. So, so this itself counts. It seems that it itself contains only the BPS, the information of the crystal. And in the BPS state counting, there is also weight associated with it. Namely, each crystal state represents a combination of BPS states. And that information is contained in these weights. So it seems to capture all the information of the BPS state counting, but in a somewhat asymmetric way. So this was a little bit more details. And so let me try to summarize. So the statement is that starting with the very general data of Quiver gauge theory with two supercharges, and together with the, in that case, relations, J terms and E terms, I constructed the model of crystal melting. It's a statistical mechanical model with a very precise combinatorics. And then also, as well as the new algebra, which we call the double Quiver algebra. And this double Quiver algebra is the, it acts on this crystal state. So it's a version of the BPS algebra, BPS state algebra, so-called in the literature. Now, this story, of course, works with n equal 4 quivers as a special case. And in that case, there was already, and when this comes from Tori-Carabiao, there was a different algebra, Quiver BPS algebra, Quiver single Quiver algebra. So I'm writing down two different algebras, and which is a little bit somewhat confusing, but it turns out that neither one contains the other. But if you extend this thing a little bit, then both of these things are included. So the relation is a little bit subtle, and, but at least that seems to be related to the fact that here, compared with the typical case, I'm turning on extra fugacity for this counting. And then somehow, at least the rough intuition I said is that this one, double Quiver algebra, counts both the particles and antiparticles. Now, now we have the new algebras and representations. And so hopefully that will interest mathematicians too. But this is a conference about the string theory, so you can ask where is string theory? well, of course, it's a version of BPS state counting. In some contexts, you can discuss the models of BPS black holes, which is non-compact, et cetera, et cetera. But in this respect, I should say that one of the motivations come from the, well, partly the paper by Kamran and others about, so we are trying to, the original motivation for this paper is that these crystals represents the so-called quantum form. So typically in string theory, we begin to see the stringy correction at some point. But in this context, we want to see more like a quantum aspect of the geometry. And the atoms I'm talking about, it turns out it's more like atoms of the space-time. So namely, we start with the atoms, and then we combine them together, and take a sample-like limit, and you're going to see the smooth geometry, as in this figure. So in a sense, the smooth geometry, it looks like a smooth geometry, but if you go into the quantum regime, there is something popping up. So that was the main motivation for this. And this whole story of the crystal melting makes it precise. And first of all, this story generalizes to the less supercharged, more general stories, and then that's one lesson from what I said. But of course, now I have a more precise algebra and everything. Well, okay, in a larger, I have a precise algebra in larger context. So you can ask, what type of lessons we can learn from this? And the short answer is that I don't know. But I just have some very preliminary comment. So which is about how the atoms fit together. So in the typical story I was presenting, and in the old work, including my old paper with Hiroshi, we are talking about the crystal melting in such a way that whenever you have a so-called molecule or everything can be constructed out of the atoms. So what I mean is that I have something complicated, but I can take atoms one by one. Or if you go backwards, you can try to construct everything, starting from single atoms and bring it one by one. And each action of the bringing it in or bringing out is represented by action of the generator. So that is the story, and it's kind of nice. Everything is like a molecule, and there is an action of the algebra which represents decomposition into the atoms. So, but we found that that structure is not always true. For example, there was a eta parameter which didn't play prominent role in my talk so far, but I changed to a different eta. And there, it happens. Sometimes you cannot create a single atom. You cannot create a single atom. You cannot add a single atom. But it is possible to two atoms simultaneously. And whether this happens or not depends on this extra data, which is called the eta. And then so this is somewhat, I'm tempted to call it speculatively, that this is more like a confinement mechanism for space-time form, in the sense that in some cases, you can create two, but only with two together. So this is one of the small examples of the lessons we might be able to learn from the algebraic structure. And this is only a small starting point, and I'm not sure what will come out. But there is a general question of if we get something extraction statement like this, is there any general lessons we can learn about the quantum gravity out of this? That's one of the future questions. And as I said at the beginning, we have to be patient. So it might take some time. But I'm optimistic that we will eventually make some further progress along those lines. Thank you so much.
Any questions for Masahito?
Historically, space-time firm has been the name given to some special types of metrics which look like these vacuum bubbles. Mm-hmm. Are there any metrics or geometries that you're associating to these?
Well, let's see. So these are, so these are more like if you have, in the original context, you have a geometry, and then you kind of geometric quantization, and then it discretizes it really. So it's not a particular metric associated with this particular point, I would say. So in a sense, the concept of metric, well, at least, well, of course, I don't really know the eventual understanding. But my idea is that it's not like there is a geometry. There is no geometry in a sense. And the geometry itself emerges. And these are some basic ingredients out of which the geometry is constructed. So in that sense, there is no metric. Yeah, so it resonates well a little bit of the idea that the gravity is emergent one way or another, yes.
Any other questions? I have one question. So in the case with two supercharges,
yes,
these formalism that you developed, what are the particular applications that you have considered in string theory? So this would be with theories in lower than 4 dimensions?
Yeah, I think that could be the target. For example, this algebra applies to Calabi-Yau four-fold compact creation, for example. And some of the nice stories go away, but at least it's an honest BPS state counting for Calabi-Yau four-folds, toric Calabi-Yau 4, for example. Or it doesn't have to be toric, but sorry, it could be other Calabi-Yau 4. And then, so what lessons we extract out of there is not clear, but we can try to, for example, study the asymptotics, and it might be a version of a black hole, for example.
And you can use these to find duality or check dualities and so forth in your...
Yeah, I think, it's a more subtle question. For example, there are some quivers which are dual, like a Seiberg dual or the triality, etc. And you can ask the question if the algebra is preserved, for example. So the algebra, first of all, the counting is the same. At least, there's a modular dependent wall crossing, etc. But as long as it's corresponding chamber, the counting itself coincides. Now, you can ask if the algebra acting on that are the same. And in some cases, we conjecture that they're the same, but there are some other evidence that in general, the algebra might be different. So algebra might be different, but the counting is the same. And but that's, so that's probably related to the picture of basically the basic degrees of freedom different when you have a duality, right? So, so these generators of the algebra represent what are the basic degrees of freedom. Basic degrees of freedom, whenever the basic particle, you prepare a generator and then construct everything. That's the idea. So in that sense, you have to reshuffle the generators from one to the other. That's the idea. So it could be that maybe if you suitably kind of confine the algebra, modulo gauge equivalence class or something, and then maybe these two algebras might be equivalent, but not among themselves.
I see. Any other questions for Masahito? If not, let's thank Masahito again for a wonderful talk.
Thank you.
Before we leave, there's an announcement.